Okay, let's start. Hello, and welcome to Math 2270, Linear Algebra. My name is Alp. I would prefer that you call me that instead of Dr. Usman or anything. So instructor. You can reach me at Usman at math.utah.edu. And before continuing any further, I should mention that I'm recording this lecture, and I'm going to try to record the rest of the lectures as well. But this is sort of like a trial. I've never done this before. This is like a one-person operation. My hope is to be able to take these recordings at the end of each week and upload them somewhere so that we have access to sort of lectures. The main reason why I think that would be good, especially for me, is because I have somewhat of a more improvisational approach. Even though I will be following the textbook, I won't be following it, line by line. So I think it would be good to have some recording of what's happening. Obviously, you guys will be left anonymous. So on Canvas, so I'm not distributing the syllabus, but you can access it on Canvas, at least a digital copy of it. Let me just mention a couple of points from it, just so that we're on the same page. So we're meeting on Mondays, Tuesdays, Wednesdays, and Fridays from 8:35 to 9:25 here. For now, I wrote office hours to be by appointment, but come next week, probably we're going to change it to some specific hour. I'm going to send out something like a survey. Course description and prerequisites. This is not, I guess one part of it is nice. This is sort of like a blurb that I wrote. Let me just read that. It is not an exaggeration to say that linear algebra is the backbone of modern science. On the one hand, many systems are modeled via linear relations. An example of this we're going to see today. And on the other hand, even when a model is inherently nonlinear, one can try to linearize it to extract information about it. So now this, we're not really going to discuss it, but in calculus, that's essentially what you're doing. Differential equations and other areas. In fact, one could say that a natural phenomenon admits mathematical inquiry insofar as it admits such a linearization, albeit possibly in a very far-fetched way. The point is that if you can differentiate something, whatever that means, you can say something about it. A big part of math is differentiating the thing and setting it equal to 0 to find the critical points or whatever. In this course, we'll start studying linear structures from a concrete and computational point of view via matrices, and eventually also develop a more abstract understanding of linearities. We will discuss and study the proofs of many theorems, such as the spectral theorem and singular value decomposition, although our main concern ultimately will be the demonstration and application of such theorems. Through this course, students will gain not only theoretical knowledge, but also practical skills relevant to real-world problems in science and technology. Expectations. So I'm not going to be taking attendance, but I expect you to attend all lectures 4 times a week. There's going to be 11 problem sets. Due Fridays, basically. The first problem set will be due not this Friday, but next Friday. There will be 3 in-class midterms on select Fridays and a final. Okay. So this is a 4-credit course, which means that based on sort of like the university regulations, let's say, you should expect to work 10 to 15 hours a week outside classes. Learning objectives. Let me just read some of them. Solve systems of linear equations, interpret matrices as linear transformations, do matrix algebra, determine and manipulate linear coordinates, compute determinants, spectral data, interpret it and compute it, determine whether a given square matrix is diagonalizable, and execute its diagonalization when possible. Essentially, spectral theorem addresses this point. Compute and interpret the inner product of two vectors. Spectral and singular value decompositions. These are sort of two of the main big theorems that we're going to discuss in this class. I think they're both in the same week toward the end. And then finally, explore a variety of applications ranging from computer graphics to signal processing and pagerank. Okay, so this pagerank is one of the examples that I quite like, and this is what we're going to start with today. You can see sort of an approximate, a tentative schedule on the syllabus. Let me not read it out. Basically, let me just say that on the syllabus you can see approximate sections from the textbook. So I separated topics into weeks instead of days, as opposed to other sections possibly that you might have looked at. So that's that. Grades, 35% from problem sets. Each of the 3 midterms will be worth 15% of the final grade, and then the remainder, 20%, will be from the final. So for the problem sets, what's going to happen is probably that the majority of the problem set will be graded based on completion. That's going to be graded by a grader, undergraduate grader, and probably I'm going to pick 1 or 2 problems that I'm not going to tell you, that I'm going to grade by myself, and I'm going to try to give sort of more feedback, and those will be, the ones that I grade will be graded based on accuracy and presentation and other things. We have this standard book. This is the book that all the other sections use in this semester. It's by McDonald. This is like a standard book. There's this inclusive access program situation, which basically makes you buy the book if you don't do anything. You should have received an email about instructions and stuff. It's not super important, but if you have any issues with that, just contact me and I'll contact someone for you, because I don't know what to do about it. Lectures, problem sets, midterms. Yeah, so the dates of the midterms are already decided. First midterm will be on February 9, which is the Friday of week 5, and then the second midterm will be on week 9, and then the third will be on week 14. And then the final exam is, its date and time is given by the university. It's going to be on May 1st from 8 to 10. Math Center, accessibility, inclusivity, and safety. All these are standard items. I'm just going to leave it to you to read all that. Academic honesty is standard. One thing perhaps, or rather 2 things that are nice or interesting, non-standard, is these 2 items, generative AI and computer algebra systems. In this course, you may use generative tools like ChatGPT, as well as computer algebra systems like MATLAB under specific guidelines. These tools are permitted to guide your understanding of problem sets and topics. When using them, you must submit logs of your interactions as part of your problem set submissions. Just be honest when you're using things. These tools can also be used to verify calculations. So let's say that I ask you to compute the determinant of a matrix and stuff like that, and you compute it by hand. So if I'm not saying anything specific, like if I'm not saying in the problem that you should be using MATLAB for this, you should not be using MATLAB when you're submitting something. But of course, after you do your calculation by hand, or before perhaps, you can use MATLAB or some other program to figure out what the solution should be, so that you have sort of like a number to shoot for. That's valid. These tools can be used to verify calculations, but remember, computations are generally expected to be done manually unless explicitly stated otherwise. You are responsible for ensuring the validity, accuracy, and relevance of your submissions, whether or not you use these tools. So it's not a valid excuse to say, oh, you know, ChatGPT told me that this is the thing. That's not really how we do things here. While encouraged, the use of such technology is not required for success in this class. The policy governing the use of such technology is specific to Math 2270-002, which is our section. Other courses and sections may have different policies. And then the regret clause is if you commit an unreasonable act, let's say cheated and something like that, but bring it to the staff's attention within 48 hours, staff being me, 48 hours of the relevant submission, sanctions may be limited to that submission only, rather than leading to further disciplinary action. This clause will not be applied in the case of repeated violations. And that's about it when it comes to the syllabus. Any questions about anything I've said? Like I said before, I'm not distributing hard copies, but you have access to digital copies to a digital copy of the syllabus on Canvas. You can go ahead and have a look. Any questions about it so far? Okay. Let's start then. I want to start with PageRank. I should say that I'm a pure mathematician by training and by what I do day by day. But as you can see from the schedule, from the tentative schedule, there's plenty of applications that we're going to be discussing, PageRank being one of them. And really, we're going to be discussing PageRank at the end of the semester on week 14. The week 14 will be specifically for PageRank. We're going to go into detail. But for now, I'm just going to use it as an example to introduce some of the ideas. Yeah, I should say that I should finish that thought, that I'm a pure mathematician and I have sort of a certain perspective on things. And I'm aware that a lot of you are computer science majors, engineering and stuff. So that's sort of like a different perspective, but hopefully we'll find a middle ground. PageRank is a certain algorithm. How many of you have heard of PageRank before? Okay, this is good. PageRank is basically the algorithm that made Google Google. Okay, this was the algorithm that they invented that basically separated their search engine from the rest at the time. So let's write it here. If you're trying to come up with a search engine, you need to do two things. You need to be able to accomplish, three things. Three steps. Step one, you first need to figure out all the web pages that are out there. The technical term for this is crawling. You have these crawlers, and somehow this crawler, these are bots basically, they just like go from link to link and figure out the network of web pages. Step two is indexing. Once you crawl the web pages and have a sense of this network of web pages, so you're literally just keeping track of the hyperlinks. You need to figure out the specific keywords for each web page that really summarizes the content of that web page. Okay? This is indexing. And then the third thing you need to do, and this third step is where PageRank really comes into play. You need to figure out, given the network structure, which web page is the most important, which web page is the second most important, and so on. Because the idea is that you want to have a search engine, so your user is going to give you sort of like a query, and you want to list all the web pages that are relevant. Somehow you need to list them. But you want to do this in a smart way, that is to say, without really going into every single web page and figuring out which one is the most important. You want to automate it as much as possible. And so this is rank. Rank the web pages. Okay? And PageRank really comes into play here. And we're just going to discuss this. How do you rank web pages in a network without really going into their content, purely based on the hyperlink structure? Okay? Let me just go over here. So the idea is this. You think of the rank, or rather, let me say, importance of a web page as something that web pages can share. So if I have one web page here, let's say Reddit. Obviously, I'm not going to write it for brevity. And let's say I have a couple other pages. Third web page, fourth web page. And let's say that this web page has a link to all the other ones. Okay? This is just a very simple example, obviously. You have to start from somewhere. So let me just repeat. This arrow here means, that's what I'm trying to denote, that this web page number 1, has a hyperlink to web page number 2. When something like this is the case, then you would say that, or this is the assumption, that whatever importance this web page has, it distributes to all the web pages it links to. Okay? So let's say that this is the importance of the first web page's PR1. Whatever this is, 1/3 of, so this is a number, 1/3 of this importance should be transferred over here. 1/3 should be transferred over here. 1/3 should be transferred over here. Okay? So I'm just going to write it like this. Add, so plus PR of 1 divided by 3. I'm dividing by 3 because this is like the total, and I'm sharing. I'm distributing equally. And then here too. Okay? But what if we had some backlinks? Let's say that not only web page 1 has a link to web page 2, but vice versa. And let's say that web page 2 also links to this, and web page 4 links to 3. Thinking of this whole importance thing as a shareable thing, from the other way around, I could say, and let me add one more perhaps. Let's say this too. To figure out what this number actually is, likewise, I would look at all the web pages that link to it. Okay? So this should have some piece coming from this, right? Whatever the importance web page 2 has, it contributes some of it to PR1, and likewise the fourth one. And so if I were to write down all these equations, I get the following. Importance of the first web page should be something. Okay. I'll go back to the board, back to there in a second. Let me just write down all these like this for now. Now we said that because the first web page has links to web pages 2, 3, and 4, to each of these web pages, it should contribute importance over 3. But this idea should apply to each other link. So to represent this, let me just put numbers here. Instead of writing it like this, I'm just going to write numbers on the arrows. I'm going to say this arrow has, so to speak, weight 1 over 3. So does this, and so does this. And then when I look at web page 2, it has a link to 1 and 4. So whatever its importance is, half of it should be sent over here, and half should be sent over here. So 1 over 2, 1 over 2. You see, 3 has no links whatsoever, so we don't have anything for that. But 4 has one link to 1, which means that it should contribute 100% of its importance to pagerank 1. Now with these weights, I can write down the equations. PageRank 1 should be all the importances coming to it, which means that it should be half the importance of the second web page plus 100% of the importance of the fourth web page. 1 over 2 times PR of 2 plus 1 times PR of 4. If I were to look at the second web page, the only arrow that goes into it is the arrow coming from the first web page, which means that PR of 2 is nothing but 1 over 3 times PR of 1. PR of 3, so it's the sum of two things. Oh, wait, I made a mistake. I made a mistake here. Because you see, from 4, there are 4 links. So I should divide it by 2. Sorry about that. Which means that this should be 1 over 2. So now this is 1 over 3 times PR of 1 plus 1 over 2 times PR of 4. And then PageRank 4 is, well, there's one arrow coming from, so one link coming from the first web page, and then one link coming from the second web page. 1 over 3 times PR of 1 plus 1 over 2 times PR of 2. Okay? Any questions about these equations so far? How I extracted them out from this hyperlink structure?
Don't you add the importance of the unit itself?
Say again?
PR of 1. I mean, it has its own importance.
Well, yeah, that is true. Yeah, but that's the genius of this algorithm. So when Google is trying to figure out which web page is the most important, it never asks the web page itself. It asks everyone around them, okay? So when I come at you and I'm trying to figure out how important you are, I never ask you. I ask all those people who know you, okay? And how I weigh them depends on how well they're known in return, okay? So this is sort of like the idea. So when I'm trying to figure out how important web page 1 is in this network, I never look at web page 1. I look at how it is connected to other things. Okay, so this is it's like an emergent, if you want. It's connectivist in terms of paradigms. Any other questions? So now let's abbreviate all this, because I don't want to keep writing this throughout. Let's just say that this is just A. It's a number, B, C, and D. If I were to use these numbers, this just becomes A equals 1 over 2 times B plus 1 over 2 times D. B is 1 over 3 times A. C is 1 over 3 times A plus 1 over 2 times D. And then finally, D is 1 over 3 times A plus 1 over 2 times B. I just rewrote this whole thing in a much more compact fashion. So this is what is called a linear system of equations. Now, as you see, even in this simple of an example of a network, we end up needing to worry about 4 different variables. The point is that we want to compute A, B, C, and D. Okay? Now, I'm sure some of you already have some idea as to how to do this. And there are really many ways of doing this. But in this class, we will try to come up with sort of like a more logistically sound way of writing the equations and writing the calculations down. Okay? Any questions about these equations so far? Now, for instance, what I can do is I can realize that the second equation tells me that, well, A is nothing but 3 times B. Well, I can just substitute, right? I can say, instead of A, I'm just going to write 3B, so that in this equation, for instance, I'm going to have 2 unknowns. And here too. And I can keep going like this. I can keep reducing the number of variables, eventually to be able to find the solution. And that is indeed a method that would work. But you can imagine how this approach would perhaps get more complicated as the number of web pages increase. Now, I don't know the exact numbers nowadays, but you can imagine that there's at least 5 billion web pages. So that means that you have 5 billion unknowns. You can still try to solve one equation in terms of the other ones and then substitute and so on. But eventually, probably this is going to get complicated and hard to handle. And so this is why one uses the so-called matrix notation to be more tidy. Instead of writing it like this, I can write it like so. And this is going to be what is called the hyperlink matrix of this network. And this, by the way, is an example now. And the way you do this is the following. You say, OK, I have 4 unknowns, A, B, C, and D. But really, what those letters are not that important. Here I wrote P, R of 4 and so on. And here I wrote D and so on. What is most important are these numbers and with what they are matched. Okay? So as long as I can keep track of those numbers, I can sort of write this in an even more compact manner. And the way you do this is the following, is like this. You say, I have 4 different web pages, and I'm going to use, because of that, a 4x4 matrix. A matrix is nothing but an array of numbers. It's a 2-dimensional array of numbers, possibly 2-dimensional. So hyperlink matrix. hyperlink matrix of this specific network. Let me actually do it like this. So this is going to be a 4x4 array. Okay. Each column is going to correspond to one of the web pages. So this first column is going to correspond to web page number 1. And what I'm going to record is, so rows 2 will correspond to web pages. And what I'm going to record in this column are essentially these weights. Because the first web page has a link to 2, 3, and 4, but not to itself, I'm going to put a 0 here. And then I'm going to list the numbers that I saw over there. So 1 over 3, 1 over 3, 1 over 3. Okay? So for instance, this entry is telling me that the first web page contributes a third of its importance to the second web page. And likewise to the third and to the fourth. So if I were to look at the second web page, this is 1 over 2, because from 2 there is a link to 1. There is no link from 2 to itself, and then there's a link to 4. Okay. 3 has no links, so it's always going to be 0. And then 4 has a link to 1 and 3. So 1 and 3. Let's denote this by capital H. This array of numbers configured in this way, so the places where I put the numbers are important, right? But this is a hyperlink matrix for this network. Okay? Now, let's also talk a little bit about this so-called random surfer model. And this is the idea behind pagerank, really. Let me write that down as well. We're going to discuss all this stuff on week 14 more in detail. This is really a very special case of what is called the Markov chain. We're going to discuss all that toward the end. But this is just like a teaser. Yeah, so the random surfer model says the following. This is something that you use to figure out the rank of web pages, to order their importance, to order web pages in terms of their importance. What you say is the following. You have sort of like this, internet surfer. It starts at a random web page. And let's say after unit time, it clicks on one of the links that are on the web page that he started at. Okay? So let's say that I started at here. If my random surfer started here, after unit time, so it spent some time in this web page too, and then after that, it got bored. So this guy got bored, so it's going to click, it's going to go to either 1 or 4. With what probability? It's going to be 50-50. Okay? This guy flips a coin, and based on the coin, the outcome of the coin, either goes to 1 or 4. And then let's say that it went to 1. And then again, this surfer spends unit time on that page 1. And then after that, again, randomly, it chooses either to go to 2, 3, or 4, and so on. It turns out this pagerank really tells you the proportions of time that this random surfer would spend on each of these web pages. That is to say, this random surfer would spend the most time on the web page that is the most important. Okay? This is sort of, there's like a jump here, I realize. But let's just keep this as a heuristic for now. And so based on this, you see there's an issue. And really, in this example, pagerank would not quite work. Do any of you have any idea as to, yeah?
Because once it got to 3, you wouldn't be able to go anywhere else.
Exactly, right? So because 3 is sort of like greedy. It has links to it, so there are links to 3, but 3 is not linking to anyone, right? So if this was sort of like the end-all be-all of PageRank, then you would just like come up with a web page and you wouldn't put any hyperlinks into it, and you would, convince someone else to put a link to you, and then you would be sort of like the best one. But that doesn't quite work. And indeed, Google, in this kind of a situation, has certain methods to deal with these kind of things. You see, this is also represented in the matrix very simply as a column consisting only of zeros. So recall that this third column corresponds to the third web page, and it doesn't have any link to any other web page. So this is what is called a importance sink. Sucks all the importance from the system, doesn't give back. But in order for PageRank to work, everything should contribute to everything else. So there should be some sort of like self-referentiality there. So let me write it. So what did I say? Rank sync. Rank or importance sync. Well, one way to deal with this is to say that if a web page doesn't have a link to any web page, I'm just going to treat it as it having a link to every web page. Okay? So if you're greedy, I'm just going to treat you as sort of like uniform. So let's say that I added these links now, just so that things work. Actually, let me not do this. For the first class, I think this can get complicated. Just leave it like this. Leave it like this. And let's just say for now that PageRank really wouldn't work in this particular example. But here's another example where it would work. I'm going to give you a more complicated example. I decided not to. Let's do something like this. Let's say that I have 5 web pages, and these are the links. Okay? So let's figure out the hyperlink matrix for it. So this now is going to be a 5 by 5 array of numbers. And let me just say that we're going to change the notation starting from tomorrow. For now, I'm just using this perhaps more intuitive notation of a table. But often you just don't write, you just don't draw these lines to separate rows and columns. 5. So could you tell me what I should be writing in the first column?
Looks like in spot 1 and 5, you'd write 1/2 to show it links to 2 and 5.
Exactly. So from 1, you have a link to only 2 and 5, which means that you should have 1/2 at spots 2 and 5, and the rest should be 0. Second one is, so from here, from 2, there's a link to 1 and 3. So 1 and 3. From 3, there's a link only to 4. So 3, 1, 2, 3, 4. Okay. From 4, there's a link to 2, 3, and 5. So 0, 1, 1, 2, 3, 4, 5. These are 1 over 3. And then from 5, there's a link to 1 and 2. 1 and 2. Okay, this is the hyperlink matrix. You see how fast it is now to write it like this, instead of first writing these equations and so on. I didn't need to write PR of letters and so on. All I had to do was to record the numbers. The numbers, which are the coefficients of the hyperlink matrix. And now you see, we don't have that problem that we had over there. Each web page links to some other web page. Now it turns out that this is still not the end shape we should be striving for. That is to say, this example could still be buggy, so that this random surfer model could get stuck at some other importance sink, but still, it's not as simple as that, at the very least. Okay, let's also finish this matrix notation. The way we're going to write this whole equation, or rather, this whole system, including A, B, C, D, the unknowns, is like this. What I'm going to do is I'm going to record the left-hand side here, A, B, C, D, into one column matrix. It's going to be one side. And on the other side, I'm going to have, again, A, B, C, D multiplied by this hyperlink matrix. Instead of writing that example, let me write this example. So I'm going to write it like so. Let's say that from A to F, I have the page ranks. Sorry, A to E. And then I'm going to have this 5 by 5 matrix. Just record everything. And then you see here, we have the coefficients as well as the unknowns on the right-hand side. Likewise, we should be seeing the unknowns on the right-hand side somewhere too. And this is how you record them. You write down literally the same matrix over here. Now we're going to discuss what this means, what writing two matrices like this next to each other means. But essentially, it means exactly this. Of course, that is for this particular example. But what I'm trying to say is that if you were to matrix multiply this thing and equate the corresponding entries on the left-hand side and the right-hand side, you get back a system of 5 linear equations that end up being the analogs of the 4 equations for this particular example. Okay? Now we're going to discuss all this stuff in much more detail. And really, has any of you seen something like this before? An equation like this before? So this is what we're going to call also an eigenvalue or eigenvector equation. Come week 10, we're going to call this the eigenvector equation for eigenvalue 1. That's, of course, ahead as well. But this is a sort of this is the sort of stuff that we're going to start building toward. And of course, the underlying mathematical sort of structures that we're going to discuss. Okay? Any questions about this? So we start with PageRank. We're going to end this course with PageRank as well in about like 3 months. Okay? Any questions, comments?
You mentioned Markov chains.
Mm-hmm.
Where does that show up in here?
Well, the relationship between the random surfer model and the fact that solving this equation, solving the eigenvalue equation or eigenvector equation for eigenvalue 1 is the Markov chain relationship. So there's a whole theory behind really that governs these types of equations. Underneath all this is this whole theory of so-called Perron-Ferrobini's operators. So we're not going to go that far, but we're going to go somewhere toward it, let's say. Any other questions? Okay, let's finish early today a little bit, a couple minutes. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So now today we're starting linear algebra proper. But before that, 2 points I'd like to make related to what we discussed yesterday. The first one is that I said something wrong on the syllabus. I corrected it now. I said that you're expected to work 10 to 15 hours per week. It's rather 8 to 12 hours. So the calculation is that per credit, you're supposed to work 2 to 3 hours outside class. So that's the correct calculation. So that's item 1. Item 2 is, I said yesterday in this second example of this web pages, this network of web pages, it is possible that PageRank doesn't work. I looked it up, actually. It does work, and there's a way to figure that out without doing any calculations, and we're going to learn about those heuristics later on. I just wanted to mention that. So, our main topic for this week is to solve linear systems of equations. We saw how linear systems of equations show up naturally, or in applications quite easily. I'm just going to start with an example. Let's consider this. I'm going to have 3 unknowns, x1, well, let's use x, y, z, and 3 equations. So the system is this. X minus 2y plus z equals 0. 2y minus 8z equals 8. 5x minus 5z equals 10. Now there's something somewhat misleading about a lot of these examples that we're going to be discussing. Namely that they're often going to involve the integer coefficients. Or possibly rational coefficients. But that is not necessarily required. It's just that calculations become somewhat more pleasant. If I wanted, I could have put here e, the Euler number, pi here, whatever. So most of what we're going to discuss are going to be really for those kind of things. But let's say this is the system. So like we discussed yesterday, we can sort of try to solve one of the variables in terms of the other ones, and then substitute that expression into the other equations and so on to simplify, right? We want to sort of reduce the number of variables in a sense. So let's try to do that for now. And then we're going to discuss how to do that in a more efficient manner too. So for instance, what I can do is the following. I can say, OK, in the second equation, I have a relation between y and z. So let me say that, so let me rewrite y in terms of z. That is to say, solve that equation for y. Sending that 8z to the other side and dividing by 2, I get this. So what is this? 4z plus 4. Maybe I should enumerate as well. So this is equation 1, equation 2, equation 3. So from equation 2, I got this. Okay. So let's call this equation 4. And then from equation 3, likewise, I can solve x in terms of z. So sending that 5z to the other side and dividing by 5, I get x equals z plus 2. And let's call this new equation 5. OK? And then now I can take these two expressions and substitute them back into the first equation. So let me write it like this. 1 plus, or let me not write plus, comma 4, comma 5 gives me this. I'm going to start with writing the right-hand side. 0 equals x minus 2y plus z. OK? So now x equals z plus 2 minus 2 times y, which is this expression, 4z plus 4. And then I have z. OK, this is good. Because you see, if I were to disregard this middle part, I have an expression, I have an equation which has only one unknown, which is z. OK? Let's sort of process this a little bit to get this. So I have z, 2z, minus 8z is minus 6z. And then 2, and then minus 8 is minus 6. So this means that this is equal to this. Well, if that is the case, sending, for instance, this minus 6 to the other side and dividing by minus 6, I get that z has to be minus 1. OK? So if z is minus 1, then I can take this expression and substitute this number back into the equation 4 and 5 to get expressions to get values for x and y. Let me do it over here. So now, well, I guess what I can do is I can say that this expression is equation number 6. 6 and 4 gives me now the following. So y equals 4z plus 4, but z is minus 1, which means that this is 0. And then if I were to take 5 and 6, well, x equals z plus 2, but z is minus 1. which is, so that means that x has to be 1. Okay? And so this calculation tells us that there's a unique triple of numbers, x, y, and z, that satisfy all three equations, all three of these equations simultaneously. Okay? Let's verify this. So let me just rewrite it again. So thus, there is a unique triple xyz. This is how I'm going to write it. This is sort of the notation for ordered tuples, ordered triples. Triple xyz, and the value is 1, 0, minus 1. That satisfies all three of the given equations. Simultaneously. Let's verify, in case you made a mistake. I might have made a mistake. Check. Well, how do I check? Any ideas? How can I verify that indeed my answer is correct, or this calculation is correct? Exactly. I have a couple numbers. I can just plug them in and see if left-hand sides equal to the right-hand side. So for instance, 1, 0, minus 1 plugged in into the first equation gives the following. 1 minus 2 times 0 plus minus 1. I should also mention that going forward, I'm not going to be this explicit about all of these calculations. But this is the second class, so I want to start slow. So the first equation is correct. Second equation tells me 2 times 0 minus 8 times z is minus 1. Well, this is 0, this is 8. Okay? So the second equation is also correct. And then the third equation tells me 5x, x is 1, minus 5z is minus 1. So that's 5 plus 5, which is 10. And indeed, it's the correct number. OK? So my calculation indeed is correct. Any questions about this? So as you see, we just use standard algebra methods. We just took one equation, solved for one variable, plugged it into the other equations, and so on. But you can imagine how this can get complicated, at least to keep track of. If I had like 10, 15, 10 billion equations and unknowns. And so instead of this, we're going to do essentially the same thing, but we're going to sort of be more smart about the logistics of it. Okay? And this is where the matrices come into play. I'm going to re-record this system of equations using matrices like this. So there are two ways of doing this. Let's do one way, the first way, which is by way of using this so-called augmented matrices. When it comes to an augmented matrix, what you do is that you just disregard the unknowns and record the coefficients, everything, in the order that you see them. So augmented matrix. So I'm just going to write it like this. And recall that yesterday I used this array. It was like a table. But now I'm not going to sort of draw lines to separate rows and columns. I'm just going to write them in an orderly fashion. Okay? So these are the coefficients coming from the first equation, for instance. And 0, because in the second equation I don't see any x. And then 2 minus 8, 8. And then 5, 0, minus 5, 10. And I like to use parentheses. Some people like to use brackets like this. I like this more. You can use either one. I should mention also that when I was first learning this stuff, it was more common to see sort of like a bar here when you had sort of like an augmented matrix. They really wanted to separate the left-hand side from the right-hand side. But nowadays, it seems this is not sort of popular anymore, so we're not going to use it. So you see, if I'm careful about where I put the numbers, and if I can do some calculations with these numbers, respecting their places, perhaps I should be able to, perhaps I can do, I can accomplish pretty much the same thing without using, you know, too much chalk, let's say. And to do that, indeed, we're going to sort of switch our perspective a little bit. Instead of solving the system by sort of first solving one unknown in terms of another one and so on, and then substituting, I'm going to try to sort of do arithmetic with each of these rows and then somehow cancel certain terms. Okay? So let me put a pause here regarding augmented matrices. Let's try to do this another way. Second alternative, second way of solving the same equation, same system of equations. Let me just say the following. For instance, I can scale the first equation by a factor of 5 and then subtract that equation from this to get rid of this 5x. Okay? So I'm going to write it like this. Replace the third equation by minus 5 times the first equation plus a third equation. Okay? So what is this? Let's compute this. Well, this is so this is minus 5x plus 10y minus 5z equals 0. And this we know to be 5x minus 5z equals 10, so that this is now, you see, x's are gone. I have 10y and then minus 10z here, and I have 10 here. Okay. So now what I'm trying to say here is that instead of using this third row, I can keep the first and second rows and then change my system so that the new system now has, instead of this 3, it has 3 prime, let's say. This is equation 3 prime. Okay? So now my new system, no system with that is equivalent, no equivalent system is this. It's minus 2. So I didn't do anything with the first row, and I didn't do anything with the second row. But now, instead of 3, row 3, I have row 3 prime. Okay? And then you see what I can do is, I can take this 3 prime and divide everything by 10. The point being that whenever I do any such operation, the solution, if it exists, doesn't change. So I keep the solution, but I change the coefficients. So now, if I were to scale this third equation by a factor of 10, and while we're at it, let's scale the second equation by a factor of 2 as well to get rid of this 2, to make it simpler. I have now another new system. I didn't do anything with the first equation. The second equation is now y minus 4z equals 4. And then the third equation is y minus z equals 1. Okay? And then, for instance, what I can do is I can take this and then add twice it to the first equation to get rid of this minus 2y. So instead of equation 1, I want to have equation 1 minus 2 times equation, so I guess, so if this is 3 prime, this is 3 double prime. Okay? So now what is this? Let me just write the whole system in a fast manner. So now, if I take the third equation over here, multiply it by 2, I get 2y minus 2z equals 2. Now I add it to the first equation so that this goes away. This is minus 2z, which means that now I have minus z. And then this is minus 2. Oh, sorry. This is 2, so that it becomes 2 again. Okay. And while I'm at it, I can also take this and subtract it from here to get rid of this y. Let me do that as well. So now 2 is going to be replaced by 2 minus 3 double prime. So this was minus 4z. If I subtract a minus z from it, I get minus 3z. And then if I subtract from 4 a 1, I get 3. Okay? So perhaps this is getting confusing. But I hope you get the idea. Somehow the steps seems to be longer compared to the first way that we used. But this method, it seems like, scales better when the matrices, or when the equations, when the number of equations grow and the number of unknowns grow. The one improvement to this system, to this method, is to just use augmented matrices, so that I don't need to sort of write all this stuff at every step, and all I need to do is to just record how numbers change. Okay? So I'm not going to finish this, but you can see, for instance, here in the second equation, we did recover z equals minus 1. And I could have gone further and used this to get rid of this and that, and so on. I'm not going to finish this, because I'm going to do the same thing using augmented matrices. Okay. Let me write this smaller.
That second one, why'd you choose -5?
Yeah, that's a good question. So the question is, why did I do this? So, because, going back a little bit, I said somehow, I thought to myself, well, in this system, the first thing I want to do is to get rid of this. But why did I decide to do that? Why didn't I decide to sort of, let's say, get rid of this? Right? Well, that's sort of like a, let me just say that there's some ambiguity in terms of the steps that you're supposed to choose, you're supposed to take in solving. There are many ways to skin a cat, and it's sort of like the same idea. You can do any sort of, you can use these steps in any way whatsoever, but as long as you're sort of following sort of like these rules that govern the rules, you get the same answer no matter what you do. Now, there are certain algorithms that really tell you at each step what exactly you should be doing, but then each algorithm sort of prioritizes something. Like some algorithm prioritizes, minimizing the errors and so on. So let's say that you're trying to do this with a computer, and your numbers are not necessarily integers, but numbers that have like some decimal places, and you can only keep track of so many of them, let's say. So depending on what you want to do, there are different algorithms. But for our purposes, all that matters is that when you see a system of equations, you can sort of like come up with a series of steps, like the ones that I've been choosing, that eventually give you the solution. Okay? Did this sort of answer your question? The point is, so the answer is that there's no reason. Ultimately, there's no reason why I started this way.
It's just kind of adjusting the equations so that they eventually simplify.
Yeah. But yeah, the point is that there are many ways to simplify it. Yeah. Okay, so I didn't finish this calculation, but I'm just going to do the same thing, and I'm going to finish it this time using this augmented matrix notation. Like I said a while ago, all I need to do is to write down the coefficients. I'm just going to write them again. So 1, -2, 1, 0, 0, 2, -8, 8, and then 5, 0, -5, 10. So our first step that we had chosen, or I had chosen, was this. The way I'm going to denote it is like this. I'm just going to put an arrow, and on it, I'm going to write down that sort of substitution, so to speak. And instead of using this notation, I'm going to use R sub 3 for row 3 and R sub 1 and so on. That's sort of like more common. R sub 3 is replaced by minus 5. Oh, sorry. Oh, yes, that's correct. Replaced by minus 5 times R sub 1 plus R sub 3. You see, in this calculation, all I need to do is to adjust these coefficients. So we first draw the matrix. I'm not doing anything with the first row and the second row. I'm not adjusting it. I'm not adjusting them. So I might as well just copy and paste everything. But the third row is being replaced by something. So if I take this, multiply it by minus 5, and then add it to here, this is now 0. OK? This becomes 10. Add to it, so that's 10. This becomes minus 5. Add to this to get minus 10. And then this has to stay as 10 because this is 0. You see, instead of doing this calculation, I recorded exactly the same no third row this way. Of course, in this notation, you now forgot the previous third row. You just replaced it. Now it's gone. But in a sense, this is somewhat more compact, as you can see. And it is much easier to follow, possibly. Any questions about this step? So this step over here corresponds exactly to this operation over here. And you see, now I wrote here new equivalent system. And if I were to look at the augmented matrix of this new system, that would be this. So somehow, this augmented matrix notation does keep track of whatever I did over here. Let's continue. Again, an arrow. So now what did I do? From this step to this step, I scaled the second row by a factor of 2. And then I scaled the third row by a factor of 10. The way I'm going to write it is like this. Replace row 2 by 1 over 2 times row 2. OK? And replace row 3 by 1 over 10 times row 3. Now, from this state to this state, I'm not changing anything with the first row. That means that I can just copy and paste it. Second one, all I need to do is to scale all of these numbers by 2, by a factor of 1 over 2. So 0, 1, minus 4, 4, 0, 1, minus 1, 1. OK? So now, again, you see, this is the augmented matrix of this system of equations. Next up, I replace row 1 by row 1 minus 2 times the third row, the latest updated version of the third row, and then row 2 by row 2 minus the updated version of row 3. So now, from that state to this state, I'm not changing the third row, so I might as well just copy and paste it. Row 1 is replaced by row 1 minus 2 times row 3. And row 2 is replaced by row 2 minus row 3. OK? So let's look at the first one here, first row. This entry is 0, so this has to stay as 1. If I were to, did I make a mistake? That should be a plus, I guess. You see, I made a mistake here, I think. I should be. That's -2. So I need to multiply this by 2. Okay, that's a plus. Good. So if I were to multiply this by 2 and add it to this, now this is 0. This is -2 now, so that's -1. This is +2, so it's 2 now. Okay, this is now the new row 1, and then this now becomes 0, 0. And then I subtract -1 from this to get -3, and then subtract 1 from this to get 3. Okay? Now, this is where I stopped on this board, but I can keep going like this. For instance, what I can do is I can scale the second row by a factor of 3, or 1/3, to get -1 and 1 here. Or if I wanted, I could do 1 minus 1. Let's say row 2 is replaced by 1/-3 times row 2 to get this. 1, 0, -1, 2, 0, 0, 1, -1, 0, 1, -1, 1. And then I can take the second row and add it to the third and first rows to get rid of these two entries. So row 1 is replaced by row 1 plus row 2, and row 3 is replaced by row 3 plus row 2. I'm not changing row 2, so it's going to stay the same. 0, 0, 1, -1. So now this becomes 1, 0, 0, because I added, and then 1, and then 0, 1, 0, 0. That's a mistake probably. 0, 1, 0, 0. Oh no, it is correct. That's good. Let's also do one final thing. This is sort of like a silly thing that you may not like, possibly, but good for computer purposes. Finally, what I can do is I can replace row 2 with row 3 and row 3 by row 2. And the way I'm going to denote this is by this. So row 2, row 3, and two-sided arrow. So that the final system is this. Okay? Now, just like we can go from a system of equations to an augmented matrix, we can go back from an augmented matrix to a system of equations. And if I were to do that with this would literally just tell me x equals 1, y equals 0, z equals -1. So converting back, to system notation, gives x equals 1, y equals 0, z equals -1. Which is exactly the same solution that we obtained. Yes?
So why did you switch the second and the third equation in the last step?
Right, so that's a good point, because if I wanted, I could have cached the system out here, right? Yeah. It's the same thing. Well, we're going to see this later. In a sense, this is, well, the reason why is because this form is nice. Because I wanted to see something like this, like a staircase.
Is that what we should look for every time to finish that staircase?
Yes,
Okay.
yes. This is like the prime shape you want to get. You're not always going to be able to get this format, but there are other sort of staircases that are sort of, again, very useful. What I really obtained here is what is called the reduced echelon form of this augmented matrix. Okay. Any other questions? Yes.
I have two questions. First question, surely that has to do with like array indexing, like when you're, writing code, like that's surely to be more predictable where the numbers are at. Is that?
I mean, you can think of it that way, yeah, sure.
The second question, like reduced echelon form, like why is the word echelon used? Like.
Well, I guess this is sort of like an echelon.
Oh, okay.
And why is it echelon? Because the leading entries are 1, and I got rid of, so this is sort of like as far as you can go. This is like the most orderly fashion you can write it, and so on. Any other questions? So these operations that I used when trying to solve the system are called the elementary row operations. Okay? It turns out that really they are also nothing but matrix multiplication. We're going to discuss this idea later. But for now, let's just understand that these are the 3 row operations. And these are, as long as you're doing these row operations, whenever you're trying to solve a system, the space of solutions or the solutions of the system are not going to change. So you can safely use these 3 operations. Let me write them down explicitly. Unless there's any other questions about this, how I solved this. Okay. Yeah?
I suppose, specifically, what are those 3 operations?
I'm going to write them just now. Yeah. So 3 elementary row operations. Well, the first one is this. It says that you can take what is called a linear combination of any 2 rows and replace either one of them by that combination. Let me be more succinct about the notation or the language. So, first one is replacement. Replace one row by the sum of itself and a multiple of another row. One row by the sum of itself and a multiple of another row. So briefly, I can just write it like this, okay? Replace row I by, let's say, A times row I plus B times row J. Okay? This is sort of like a shorthand for this expression. Second, what else did we see? Well, I replaced a row by a scaled version of it. So that's the second operation. Scaling. Oh. Multiply all entries in a row by a non-zero constant. by a non-zero constant briefly, I can just write it like this. Replace row I by a times row I. Now, maybe I should ask this. Why is there this word non-zero? Why can I not just use a zero constant here?
Is it because multiplying by zero kind of doesn't tell you anything about the original equation? It just sets it to zero.
Yeah, not only that, but you're actually losing information, right? Because if I were to take, for instance, at this stage, if I were to multiply the second row, I would just zero all of these entries, but then I lost information, right? That's why you cannot multiply by a zero constant. And then the third one is this third operation here, which is a swapping or interchange. Let me write it over there. Interchange two rows. And briefly, I can just write it like this. Ri, two-sided arrow, Rj. OK? So the big idea is that as long as you're using these three operations to modify an augmented matrix, then the solution of the system that corresponds to the augmented matrix is not going to change. So let me just briefly say this. Key idea: elementary row operations preserve solutions. Let me just say it that way. Preserve solutions. Okay? Which means that you can use these elementary row operations to process the system, to put it in a much more convenient form, to just read out the solutions. Okay, that's the idea. Now, which steps to choose, and whether or not you can be optimal about the number of steps and stuff, that's sort of like a complicated, quite interesting topic. We're not really, I don't think I'm going to discuss too much about those intricacies. For us, at least at this point, what matters is that you can successfully do these three operations and really to use them to solve systems and find if systems have no solutions, which might happen. Any questions?
What would it look like if a system had no solutions?
Well, think of it like this. All this that we discussed applies to two equations with two unknowns. Okay? But I can interpret an equation with two unknowns as the equation of a line in the plane. This is sort of like the geometric understanding. So ax plus by equals c, dx plus ey equals f. Let's say that here a, b, c, d, e, and f are given coefficients, x and y are unknowns. Okay? Each row here can be interpreted as a line in the plane. Well, if I have two lines in the plane, there are three options that can happen. Either this happens, or really this happens. In this case, you have a unique solution. In this case, you have no solutions. In this case, you have infinitely many solutions. The same thing, or somewhat more complicated versions of this, does happen in higher dimensions, in more equations and so on. So if this is sort of a line in 2 dimensions, if you had more unknowns, you would have a plane and so on. And then you would think about their intersections. And likewise, you would have either unique intersections, no intersections, or infinitely many intersections. Of course, we're going to be also discussing the exact shape of that space of intersections as well. That's going to come ahead. That's going to be ahead. Okay? Thank you. I'll see you tomorrow. Let's start. Good morning. So now today we're going to do some more row reduction, and we're going to discuss a little bit more about these echelon forms and stuff, and then hopefully we'll have some time to switch over to vectors. And a couple of you already asked, so on Canvas the problem sets have web pages as they're like assignment web pages, but they're empty. As time goes by, I'm going to populate them with the problem sets. Typically, you're going to have around a week to work on any given problem set. Okay, and of course, given the other sort of exams and stuff, I designed this class so that at any given time, you have only one outstanding thing. Either you have a problem set that you're working on, or you have a midterm that you should be worried about, or not worried about, I guess. So the first thing I want to do is I want to mention this matrix vector notation. Okay, so this was the example that we discussed yesterday. Maybe I should do some other one, actually. So let's look at this. This is a new example. So it's a system of equations. Y minus 4z equals 8. 2x minus 3y plus 2z equals 1. 4x minus 8y plus 12z equals 1. Now, I'd like to use this row reduction stuff to really solve this as well. But before going into that, let me mention two things. So this is the system notation, right? This is a system of 3 linear equations with 3 unknowns. So this is the system notation. And yesterday we learned about this augmented matrix notation. I'm going to write it here because that's the one that I'm going to use to solve it, really. And so if I were to switch this, or if I were to switch over to the augmented matrix notation, no. Now, all I need to do is to record the numbers only, and I need to be careful about where each number is. So 0, 1, minus 4, 8 is the first row. And then second row is 2 minus 3, 2, 1. And then the third row is 4 minus 8, 12, 1. Okay, this is the augmented matrix notation. Now, in a second, I'm going to use this to solve the system. But let's also mention this third notation, which is the matrix vector notation, or matrix notation. Well, let's say matrix equation notation. Equation notation. So in practice, I use this more often in my own research. I find it more convenient. But the idea is this. This is just sort of like an anonymous matrix. It just contains some numbers. But perhaps it might be better to record this system as an equation. I want to have a left-hand side and I want to have a right-hand side. Now, we use this on Monday too. I sort of use this notation to write down this pagerank equation. So let's do the same thing here. What I'm going to do is the following. I'm going to have a left-hand side and a right-hand side. I'm going to store the right-hand side in a column matrix. So 8, 1, 1. So this is a 3 by 1 matrix. And then I'm going to record the unknowns too in a column matrix like this. X, Y, Z. And here, I'd like to have the matrix of the coefficients coming from the left-hand side. So this is going to be 0, 1, minus 4, 2 minus 3, 2, 4 minus 8, 12. Okay, you see, this is yet another way of writing the same thing. And as you can see, the augmented matrix notation and the matrix equation notation are somewhat related in that you take this, for instance, you erase all this stuff and you adjoin this coefficient matrix and this right-hand side matrix to get the augmented matrix. And if you wanted to go backward, you would just split it. Now, there's a reason why I put this matrix here and this here instead of some other place. We're going to learn, come next week probably, no, come week 3, that this really is an instance of matrix multiplication. And if I were to multiply this matrix, I would get yet another 3 by 1 matrix whose rows are these 3 expressions. We're going to get to that later, but for now, let's just take it for granted that I can rewrite this like this. And you see, this also allows me to be more specific about the unknowns, what their names are. Okay? Now, this is not the only way of writing this in terms of matrices. There are other ways of doing this, but let's just keep it like this for now. So if I wanted, for instance, I could have put this matrix of unknowns on the left-hand side, but I would need to change pretty much everything here. Their shapes would need to be changed. So for now, let's leave it like this. Any questions about this? It's just a different way of storing the information. Okay, so now let's try to solve the system using this augmented matrix notation. I'm going to use row operations. So for instance, what I can do is this. So this is the 1. Okay, let me think about this. I can do a couple of things, right? So I can say I want to get rid of this first, and I can say I'm going to multiply this by 2 and then subtract it from here, and so on. There are multiple ways of doing this, but perhaps a different way I can do is the following. I can take this, the first row, add it to the second row 3 times to get rid of this. and then add it to the third row 8 times to get rid of this. Okay, that's what I'm going to do. And recall the notation was this. R2, row 2, is replaced by row 2 plus 3 times row 1. And then R3 is replaced by R3 plus 8 times row 1. Okay? So now I have this new augmented matrix. First row, I can copy and paste. Minus 4, 8. So this entry is 0, which means that no matter what I do here, these two are going to stay the same. Let me just copy them as well. Now, these two are going to be 0. So now I need to compute these 4 entries. Okay? If I multiply this by 3, I have minus 12. Add to this, I get 10. Multiply by 3 is 24. Add to this, 25. So now from here to there, I'm multiplying by 8. So multiply by 8 minus 32. Add to 12. I have minus 20. 8 times 8 is 64. Added to 1 is 65. Okay? I just decided to choose this step. Why am I doing this? Because I'm trying to sort of get as many zeros as possible. Think of it that way. Now what can I do? Okay, let's do the following, for instance. Let's multiply this by minus 2 and add it to this. So R3 replaced by R3 minus 2, R2. First row stays the same. Second row stays the same. Third row now is going to be 0 here. Here it's going to be 0. If I multiply this by minus 2, I get minus 20. But this is also minus 20. So that's minus 40. Multiply this by 2, I get 50. If I subtract it from 65, I get 15. Okay? So I obtained yet another 0 over here. Now, next thing I can do is to simplify the calculations a little bit. I can scale the third row by 1 over 5. Can I do something else? Let's do it like this, actually. Let's swap the rows so that I have first this row, and then this as a second row, and then this as a third row. So the notation for this is R1, two-sided arrow, R2. Okay. Recall from yesterday, we had this idea of obtaining this staircase. And this is a staircase right now. So this is sort of something that we would want. And we're going to call such forms echelon forms. I'm going to discuss this in a second in more detail. So this is now in echelon form. Okay. Now at this point I can cash out my system notation to get the solution, but I can go further as well to simplify the expressions. One thing I can do, for instance, is to scale the first row by 1 over 2 and scale the third row by 1 over minus 40. The point here being that at each of these steps, I would like to get a 1. So replace R1 by 1 over 2 times R1, and replace R3 by minus 1 over 40 times R3. And I'm not going to do anything with the second row. So this is 0, 1, minus 4, 8, 1, 0, 5, 25 over 2. If you wanted, you could have written it as 12.5, but it's not that important. And this is 0, 0, 1, minus 15 over 40. And I can simplify that to 3 over 8 with a minus.
That first transition from the first to the second, wouldn't that become negative 10 instead of positive 10?
Well, if that is true, then we're in a better shape. Let's figure that out. So there's an objection, okay? Your colleague is suggesting that I made a calculation error. Let's see. So you're saying that this is wrong.
The one above it.
Oh, this is wrong.
That should be negative 10.
Okay, so if I add 3 times this to this, yeah, you're right. You see, I have to multiply this by 3, so now it's minus 12. And then if I add it to this, I have minus 10. Okay, so now, of course, this error is going to trickle down. From here to there, I didn't switch the second row, so it stays the same. From here to there, all I did was to switch the rows, so this becomes a minus 10. And then from here to there, all I did was divide it by 2, so now this is the entry. Okay?
The R3 minus 2R2, that would become 0, wouldn't it?
R3 minus 2R2. Oh, I added this to this. You're right. So now this is 0. Then this is 0. Oh, okay, so now I need to change this. Because instead of now this pivot, you see the echelon form is slightly different. The new echelon form is like this. The correct one. And so now I would need to scale the third row by 1 over 15. Okay? Yes?
So how does that work then if you have like all zeros? Because if you switch it out for like system notation, you have 0 times x times plus 0 times y plus 0 times z equals 1, right?
Mm-hmm. So what does that mean?
That there is no solution.
Exactly. There you go. So yesterday we sort of mentioned that sometimes you have a unique solution, sometimes you have infinitely many solutions, and sometimes you have no solutions. It turns out that if I were to cash this out back into a system, back into the system notation, the first row would say, x minus 5z equals this number. That's fine. Y minus 4z equals 8. That's also fine. But then this third row, according to our understanding of conversion, would just say that on the left-hand side, I have 0. On the right-hand side, I have 1, which can't happen, which means that this system has no solutions. No solutions. Now, as opposed to the example that we discussed yesterday, I hope now we can perhaps start appreciating more this augmented matrix notation. Now, of course, if you have a unique solution, you can sort of like try substituting one equation into the other and so on to find it. But how are you going to keep track of whether or not something even has a solution, right? Just because numbers are written down doesn't make it that the system has a solution. Any questions about this? Yeah.
So do you only need to see that once, like a contradiction like that, in
Yeah.
order to know
Yeah.
the whole thing is just
Yeah.
valid?
Yeah. So let's introduce some terminology. I'm going to call a system either consistent or inconsistent, depending on whether or not it has a solution or not. System. Inconsistent if zero solutions, no solutions. Consistent if it has at least one solution. Let me just say otherwise. Now this in itself has two subcases. Either it's going to have a unique solution or it's going to have infinitely many solutions. Okay? So now yesterday we saw an example of this, and this example here is an example of this. Let's see an example of this. Unless there are any questions. So consider this. So this time I'm going to start with an augmented matrix already. Okay? I'm not going to bother with writing down the system of equations. So let's say that the augmented matrix is this. So six, 4, minus 5. So in this notation, this is sort of like the right-hand side. And I have like 1, 2, 3, 4, 5 unknowns. 3 minus 7, 8, minus 5, 8, 9, 3 minus 9, 12, minus 9, 6, 15. Now this example is covered in the book. They just go through this row reduction algorithm in a very precise manner. I'm not going to follow this. I'm just going to tell you what they end up with, okay? The reduced form. So row reduction gives the reduced form, echelon form. This 3 minus 9, 12, minus 9, 6, 15. 0, 2, minus 4, 4, 2, minus 6. 0, 0, 0, 0, 1, 4. Okay. Now this is in echelon form because I get to see this staircase. Okay. So what's the point of these staircases? How do I determine them? Underneath these staircases, I should be able to see only zeros, and above some numbers. On top of that, these entries should be non-zero, and likewise here you see these entries are non-zero. So these have to be non-zero, and below these, below the triangle, below the staircase, you should be seeing zeros. So that's why it's the echelon form. And then if you continue this calculation, you get the reduced echelon form, where instead of this you have this shape, and let me write that down as well. So this is now reduced echelon form. Oh, it's not quite reduced. Sorry. It's not quite reduced. We'll get to that in a second. So the reduced echelon form for this is this. Further row reduction gives reduced echelon form to be this: 1, 0, minus 2, 3, 0, minus 24. 0, 1, minus 2, 2, 0, minus 7. Then finally I have 0, 0, 0, 0, 1, 4. Okay? So now, you see, between the echelon form and the reduced echelon form, what is shared is this staircase. It's in the same shape. It has the same shape. The difference is that the leading entries here are, instead of some numbers that are non-zero, always 1. So you normalize these steps of the staircase. And on top of that, above these steps, you always see 0 too. You see? Here you see 0, and here you see zeros as well. As opposed to minus 9 here, 6 and 2 here. Okay? So this is just some terminology. Yeah, let's finish this example. Cashing out the system, let's say that the variables are A, B, C, D, E. Okay? So now, in system notation, I have A minus 2C plus 3D equals minus 24. That's the first row. Second row tells me B minus 2C plus 2D equals minus 7. And then the last row says A, B, C, D, E equals 4. Okay? So we figured out a unique number value for the variable E. But how about the other ones? So what can we say about this? Any ideas? Like, what is going on and how can I continue further? You see, at this point, let's just stipulate that we did everything we could and we ran out of information. Okay? There is no further information for you to determine ACD and BCD as specific numerical values. All you can do is to get these expressions. So it's because of that, I'm going to think of it like this. You see, I'm going to send these two to the other side and these two to the other side as well. And rewrite this like this. So instead of writing it like that, I'm going to write it like so. So E is 4. That's fine. A is 2c minus 3d plus 24. B is 2c minus 2d equals minus 7. C is question mark and D is question mark. The benefit of this form over that is this. I can interpret it like so. I don't know what C is and D is, and consequently, I don't know what A is and B is. But if I were given what C is and D is, that information would completely determine what A and B are. So because of that, instead of writing this like this question mark, the term of art is to say that this is free. It's a free variable. The information given to you does not allow you to further specify what C is. And D too is free. And A and B are completely determined once these two free variables are determined. Okay? So this is now the general solution. This is a solution of the system. But whenever you have free variables, that means that you can choose whatever number you want for them, which in particular means that you have infinitely many solutions. Okay? So if you have at least one free variable, means infinitely many solutions. Okay? You can also think of the number of free variables as a degree of freedom. In this case, I would say that the degree of freedom is 2. This is two-sided, really. And this too. Okay. So this notion of degree of freedom, we're going to later on call dimension. Okay. So this is also called dimension. So really, geometrically speaking, and we're going to learn how to interpret all this stuff geometrically as well, the space of solutions, so all 5 tuples that solve this system, if you wanted to visualize them, would be a plane in a 5-dimensional space. Okay? So we're going to get to that later. For now, this trichotomy is what we need. Any questions? And again, you see how this augmented matrix notation makes it more convenient when you have infinitely many solutions. Because you see, if you didn't use this augmented matrix notation, you would end up needing to sort of carry around all these free variables. And you wouldn't really, so you would only see that they are really free at the end. So this is also yet another reason why it's good to use augmented matrices. Questions? Now, given this, let's get back to this open issue. I wrote earlier that this is in reduced echelon form, and then I stopped myself. I said it's not quite in reduced echelon form. Can you now tell me why I stopped it and it's indeed not in reduced echelon form and something like that? Like, what are your thoughts about this? Why is this not in echelon form, reduced echelon form? Hmm? Exactly. You see, we said that the rule is that when you have a stair, it has to be 1, and above it, all you can see is a 0, or zeros. But then when you look at this, you see I have non-zero entries there. So let's finish that up and turn that into reduced echelon form as well. So example 1. Oh, this is continue from example 1. Okay. Yeah. Okay. So this is not in reduced echelon form, not in reduced echelon form, but I can take it and reduce it. 1, 0, minus 5, then what is that? 25 divided by 2. And then I have 0, 1, minus 4, 8. And then I have 0, 0, 0, 1. Now, eventually, I mean, possibly in problem set 1, you're going to have a problem that is asking you to row reduce a matrix. But eventually, perhaps after the first midterm, I'm not going to ask you to record these row operations. You can just do it by hand, or you can just eyeball things, and you don't need to really record and tell me what exactly is going on. So at this point, I could literally say that, oh, I can just take this, get rid of these two. So the next stage would be 1, 0, minus 5, 0, 0, 1, minus 4, 0, 0, 0, 0, 1. Okay, this is perfectly valid. But for now, let's be specific about the exact operations that we're doing. What did I do? I took the third row and added minus 8 times it to the second row. And again, I took the third row and added minus 25 divided by 2 to the first row. So row 1 replaced by row 1 minus 25 divided by 2 times row 3. And row 2 is replaced by row 2 minus 8 times row 3. So now this is in reduced echelon form. Okay. You see, stairs are 1. Below, I see zeros. Above the stairs, I see zeros. Any questions about this? Like 10 minutes. Now, at this point, I should again mention that really I don't really want to emphasize too much these different algorithms and stuff. It's good to know something, but I would suggest that whenever you see a linear system or an augmented matrix and so on, and whenever you're asked to row reduce it, just think of it as an art. Try to do as many examples as possible to just get accustomed to the row operations. That's the most important thing at this stage, I think. I'm not going to give you the precise description of what it means for a matrix to be in echelon form or reduced echelon form. Instead, I'm going to list all possible echelon forms and reduced echelon forms for, I think, 2 by 3 matrices. And I should mention that I'm aware that right now I'm fast forwarding all this stuff. That's because we have we have things that are harder to digest coming up. So I want to spend more time on those. That's why I'm sort of fast forwarding this row reduction stuff. So all possible echelon forms in, let's say, 2 by 3. So I have 2 rows, 3 columns. Well, you have to start from the beginning. This is a valid echelon form, okay? And this is a stair. This is a staircase. Now I could have sort of like one kink over here. And I'm going to use the notation of the book. What they use is this, okay? They use a black box or filled-in box to represent a non-zero entry. So here's a legend, filled-in box, non-zero number. That's a stair. Or I could have a non-zero entry here. And here, I can have any entry whatsoever. So the book uses star for that. So star could be 0 or non-zero. So star, 0, or non-zero number. Or I could have my entry here, and then 2 stars, and then 0, 0, 0 in the second row. Okay. We're not done. I can further modify this and have here a kink. So now this turns into this. And here I have 2 options. Either I have a kink here or here. Okay. The way I think about it is sort of like Tetris, okay? Things are coming from here, and these are like tetrominoes. Okay? Think of it that way. So these are the all possible echelon forms for 2 by 3 matrices. How about the reduced echelon forms? Now the structure will be the same, but I have to process each of these entries a little bit, just like I did over here. All possible reduced echelon forms in 2 by 3. Let me just write all of these down, and then I'll describe them. Oh, that one. Sorry. Okay. So as you see, the tree structure over there and here are the same, is the same. What's the difference? For instance, from here, I went over here by first making sure that all of these non-zero entries are really normalized to be 1. And then I said, oh, possibly the start is 0 or non-zero. In any event, I want to take this and get rid of it so that I have a 0 over here. Okay, that's the only difference. The benefit over this over that is that given any matrix, its reduced echelon form is unique, whereas its echelon form is not unique. Okay? So is not unique. Reduced echelon form is unique. Okay. Now let me ask, why is it the case that the echelon form of a matrix is not unique? Any ideas? So let's think of an example. Let's say that I have this matrix. Here's an example. For instance, 2, 1, 0, 0, 1, 2. Now this is in echelon form. It's not in reduced echelon form. I'm saying that I can do a row operation to this, keep the echelon form, but it would be a different matrix. For instance, what I can do is I can multiply the first row by 2. Okay? So that I would get 4, 2, 0. This is what is called a row equivalent matrix to the original one. Okay? Maybe perhaps write it like this. Both of these are in echelon form. Neither of them are in reduced echelon form, but they are row equivalent. So I can go from one to the other using a row operation. You see, that's why this echelon form is not unique. But if I were to turn this over to the reduced echelon form, so this is the echelon form, this is the reduced echelon form, this would be a 1, and then this would be 0 because I would just use this to get rid of this, right? So 1, 0, 0, 0, oh, sorry. Oh, yes, that's correct. 1, and then 2. The reduced echelon form of this would be this. Okay? So this would be unique. The point is that because on the stairs you have ones, you can't sort of like scale the rows to get something else. And because above the stairs you have zeros, you also cannot take a row and add it to some other row to do something. So that's why this would be unique, whereas these two wouldn't be. Okay? This is sort of like a minor point. Just wanted to mention it. Okay, any questions about any of this? Now at this point you have, this is like all I wanted to say about row reduction. Now it's your turn to do as many exercises and examples as possible to get accustomed to these operations and so on. This is sort of like the basic arithmetic in a sense of this class. Questions, comments? Okay, I'll see you on Friday. Thank you. Okay, let's start. Good morning. So problem set 1 is on Canvas. I just wanted to say a couple of words about it, the whole like structure of it. So, so there's a bunch of problems there, 10 of them. And many of these problems I've taken from the book, but possibly I've adjusted them a little bit. Added some more like what is called flavor text, I guess. So most of these problems are going to be graded based on completion, and probably 1 or 2 of them will be graded based on accuracy. And there's a bunch of things about generative AI and computer algebra systems to the extent that you can use them and so on. The main idea is that if you're going to use these technology stuff, you have to be able to share the logs of what you've been doing with those, and you shouldn't be asking exact answers. What else? Yeah, so, and the way I want you to submit these problems or problem sets or your work is first to, so once you're done with the problems and you're done with writing them and so on, there's going to be a Google form and there's a link on the problem set specification that you can see. I want you to fill them out. And this is basically sort of like a self-reflection plus reflection on the problems, which ones are easy, which ones were easy and hard, how am I doing, and like what you would like changed, and a lot of these things. And I'm also sort of asking about your sort of like how you've spent your week working on the problem set. For instance, there's a question which asks, on which day of the week did you first have a look at this problem set, and so on. These are just to sort of, so I want to know how things are going, and hopefully we're going to sort of like be able to learn how to learn and learn how to study math as well. And so here I drew some graphs. Okay, so this is the time versus work graph. Starts from Friday, ends at Friday. This is like a weekly cycle. And this is the time versus frustration graph. Ideally, you want to, so there's of course an upper bound on the amount of work or number of hours you can spend. It's 24. But I would suggest that you also have a lower bound. Okay. So start today. At least have a look at the problems so that it's in the back of your head and you can start thinking about them, okay? So you want to have something like this. You want to have something like this. What you don't want is this, okay? All week you don't work on it, and then on Thursday night you start working on it, okay? Now I understand that you have many other classes, etc. as well, but believe you me, if you do this red strategy, the area underneath will be larger, okay? You're going to end up needing to work more. So do it like this, work a little bit every day, starting today. And a lot of these problems, I'm designing these problem sets to be, hard. It's like you shouldn't be able to just go at it and like complete it in one sitting. It should take multiple sessions. You should be able to, you should need to sort of sleep on some of the problems and so on. And so this is sort of like the frustration versus time graph. Let's say it should be something like this. Let's say you start at here, and then as you start working, it should increase. But this is sort of like the graph that you should expect. Eventually, it's at the end of the week, it shouldn't be 0, but it should be much less. Now, if you do this, what's going to happen is this. Because you're avoiding, you know that you're avoiding the problem set, you're already going to be frustrated. And then it's going to be like this. And then once it hits Thursday night, and you start sort of like cramming things, you're going to realize that it's much harder than you thought. And this is just going to blow off, okay? So don't do the red lines, do the white lines. Work a little bit every day. Sleep on the problems. And I would also suggest that given any problem, just spend like 15 to 20 minutes at first, just to get a sense of what is going on. Try to play with it, experiment a little bit, and so on. And just leave it. And then perhaps next day, try it again. And if the next day, again, after 15, 20 minutes, the problem seems like it's not budging, send me an email, okay? So there's a reason why I'm here. You should be asking me questions. Just like if you're getting too frustrated, just contact me and we'll try to figure something out. Okay? Any questions about this? Okay. So this is what I wanted to say. And so this is going to be sort of like the weekly, cycle. Typically, you're gonna get the new problem set each Friday, and then you're going to have around a week to work through it. Okay. So today I'd like to discuss another major actor in this class, which is called a vector. Vectors. Now, for now, we're just going to take a vector to be a special type of matrix. Maybe I should back up a little bit. How should I say this? Let's put it this way. This is sort of like a circular definition, but a vector is an element of a vector space. So you don't really take a thing and call it a vector. That really doesn't make anything. That doesn't really make much sense. What is important is that you have a bunch of vectors that work together. It's like a number system. For us, the most important vector space for now, the quintessential example, will be the Euclidean space. Euclidean vector space. And the notation for this is R to the n. Okay? So this is just R. It's called Blackboard bold. This is like how you write a bold R letter on the blackboard, or one way of writing it. And n here tells me that this is an n tuple. So this contains, so the vectors in this are n tuples. So let me write it here. Vectors in Rn are ordered n tuples of real numbers. So the standard notation for this is, you can say, for instance, V, a vector in R, n, means that I can write it like so. V equals V1, V2, V3, dot, 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 Vn. Okay? So here Vi are going to be numbers. Now the convention is that vectors like this are the same thing as column matrices. That's why I was saying that vectors are special matrices. So vectors are identified with column matrices. And by a column matrix, all I mean is a matrix that has only one column. So B equals V1, V2, V3, Vn. This I'm going to think of as the same thing as B, V1, V2, V3, Vn. Okay? Now later on, in a couple of weeks, we're going to sort of discuss what this really means in a more formal sense. So the word we're going to use then is going to be isomorphism. But for now, let's just think of it as identified. So I can store a vector as an ordered tuple, or I can store them. I can store it in a column matrix like this. Now, what does this allow us to do? We can do two things, two fundamental things with vectors. And going forward, I'm just going to use this notation. We can do two things with vectors. Insofar as they are vectors in the same vector space, that is to say, they're both elements of this Rn. The first is addition. Things with vectors. One, vector addition. Well, if I have V and W, two vectors in Rn, then their sum, which I'm just going to write it like this, is going to be yet another vector whose entries are the sum of the entries, the sums of the entries. Up. V2 plus W2 dot 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 Vn plus Wn. Okay? So another way of thinking about this is that perhaps I should write it like that. So V plus W is, using this notation, the same thing as V1, V2 dot 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 Vn, this column matrix, plus W1, W2 dot 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 Wn equals this. I should also mention that because we're thinking of vectors as column matrices, you're also going to see this terminology. They're just going to call them column vectors. So AKA okay. So you see I have one vector, another vector, they are of the same dimension. And the way I add them is by entry-wise. Okay? And I store the results there. That's the first operation. The second operation is called scalar multiplication. For scalar multiplication, I'm just going to use one vector. And one number. Let's call it, let's use the notation C, number. And then I want to have a new vector called C times V. So writing it out, we have this. And just like regular multiplication, number multiplication, often we don't put any notation here. And so this multiplication is just going to be the vector whose entries are the multiples of these. And I'm going to use this number. So this is c times v1, c times v2, and so on. Okay, these are the two fundamental operations. Okay, so you can think of these as generalizations of regular addition and regular multiplication. But of course, there's one caveat. In order to really understand why we're sort of defining these this way, we should think of regular addition and regular multiplication geometrically. That is to say, as an ancient Greek, or a person who was living in ancient Greece, who was educated. So let me write it like this. Vector addition and scalar multiplication generalize number addition and number multiplication interpreted geometrically as follows. Maybe I should ask this. How can I interpret number addition geometrically? Like, how can I interpret 5 plus 3, for instance, geometrically?
I would guess, like, if you had a coordinate plane, you'd have one line 5 units long, another line 3 units long, and then you produce a new line that's 8 units long.
Exactly, right? So you have sort of like a little rod. Let's be even more physical. You have a rod that somehow you decided is 5 units long, and then next to it you put another rod and you sort of like glue them together. You have another rod that is of length 3, and then if you put them together, you get yet another rod that has 8 unit lengths. So okay. Now, how about multiplication? And so this is somewhat more easier part of this sort of exercise, let's say, thought experiment. How about this? How can I interpret this geometrically? Now, there's more than one way of doing this. Yeah.
You just take 5 of the, or 3 of the 5 like things and put them next to each other.
Exactly. So in terms of rods, I can think of it like this. You know, this perhaps starts breaking apart when you start thinking about 5 times pi. Like, what does it mean to take pi many of 5 and so on? So another way of thinking about it is sort of, let's say you have sort of like a rubber band, and you take it and you stretch it by a factor of 3, and that's what you get. The point is that the unit of this and the unit of this are the same, and at the end you get the same unit. So you get something of the same unit. Let's say this is length, this is length, and at the end you get length again. Here, this has length, so as the unit, and this too has length as the unit, which means that this number is dimensionless. It's a sort of abstract number. Because if this also had length, the geometric interpretation would be different. It would be area, right? So let me write this. This is important. So this number is dimensionless. Of course, it depends. So that this is the case depends on the fact that I first started with saying that I have a rod of length, or I have a rubber band of length 5 units. I could have said I have a rubber band of length 3 units, and then this would be dimensionless. The point is that not both of them have dimension. And if I thought of this number as having dimension as well, then by sort of like dimension analysis, if you're multiplying two things, both of which have units length, then the end result would be length, would have the unit length squared. Okay, this is important. So had unit then 15 would have unit L squared. That is to say that 15 wouldn't be a length, it would be area, i.e. it would be an area, something that is fundamentally different, or it would be something that has an area. Because if you were to think of 3 as having a unit as well, the geometric interpretation for that would be this. It would be a fundamentally different phenomenon as compared to this. Okay? So now, vector addition and scalar multiplication doesn't really consider this case. It considers this and this. Because you want to end up with something of the same type. Okay? And for this reason, this number is called, so such numbers are called scalars. That's why it's called scalar multiplication, because you're using them to scale. Okay? Any questions about it? Yeah.
So then if we were to, like, I guess we probably won't do this, but if we multiply two vectors together, then would that be like the second case where you would almost?
Well, there are multiple ways of multiplying vectors.
Well, yeah.
So let's not get to that for now. But yes, so in a sense, it is true that there is a multiplication. There's a notion of vector multiplication that does correspond to this. That is true. But that is not the only vector multiplication. Yes?
Why is it called Euclidean?
Convention. You don't need to call it Euclidean vector space. I just like calling it that. I mean, you can say Euclid came up with it or something. I don't quite know. It's not substantial why it's called Euclidean, I think, for our purposes at least.
Would it be correct in calling it a vector field?
Well, you could call it that. I bet there are some people who do call it that, but in this class, because I'm a mathematician, vector field means something different for me, so we're not going to call it that. And also in the book, they don't use that terminology. Any other questions?
So the reason that number is a scalar is because it is not having any dimensions associated with it. It's just a number.
Yes,
That's why.
it's just a number.
Cool.
Yes.
Calculus was the mouse one. Or I didn't read it.
Okay. So now let's introduce some more terminology. Or maybe before that, let me sort of supply all this stuff with some further geometric intuition. I'm going to actually think about why this is called Euclidean and look into the literature. I don't know. This is like a historical question, of course, but I don't know the answer to it. I'm going to have to look into it. So. Euclidean. Oh, here's one speculative answer. Because, you know, Euclidean geometry is all about things that are happening in the plane or like three-dimensional space and so on. Perhaps that's why. Because like in modern math and science in general, we also have curved spaces. So those are non-Euclidean, for instance, non-Euclidean geometries. They're not flat, in a sense. That could be one reason. But I'm going to have to look into it and get back to you. So, so what happens if n is equal to 2? Then R2, right, is just the collection of pairs of numbers. So, collection of pairs of numbers. And of course, this corresponds to the plane. I'll just call it the Euclidean plane. Okay? Now, here's what I can do. I can say, okay, so if I have a vector now in R2, it's going to have 2 entries. I can interpret the first entry as the x-coordinate and the second entry as the y-coordinate. So here's v1, here's v2. And this point right there is v. It turns out that instead of thinking of v as a point, it's better to think of it as an arrow from the origin. So instead of thinking of it like this, I'm going to think of v as this. Okay? Now the word vector is cognate with words like vehicle. So it contains some information about motion. And so instead of a point, that's why I think people sort of use arrows to represent. V, the vector, is really telling me something about where I should be going. And with what magnitude as well, but we're going to get to that later. And further, if I think of a vector like this as an arrow starting from the origin, ending at the coordinates determined by these numbers, then vector addition and scalar multiplication too end up having nice geometric interpretations. So let me write it like this. Addition and instead of using this abstract notation, let me just be more specific and use just numbers or numerical values. So let's say that B is 1, 2, and W is -1, 3. Okay? So now, what is V plus W, algebraically speaking? All I need to do is to add the entries. Let me do this explicitly at least once. So 1 minus 1 is the first entry. And then the second entry is 2 plus 3. And I have only 2 entries. So the end result is yet another vector whose entries are 0 and 5. Geometrically, I can do this. So continuing this example from here, let me try to be somewhat more accurate with my visualization. I need units. So 1, 2, 3, 0, minus 1, minus 2. And then 1, 2, 3. And that's probably all I need. So v is at 1, 2. That means that the x-coordinate is 1 and the y-coordinate is 2. So this is the endpoint. And I'm thinking of v as this arrow starting from the origin. OK? And then the second vector has entries minus 1, 3. So the first coordinate is minus 1. Second coordinate is 3. So the endpoint is here. And again, I'm thinking of w, this new vector, as yet another arrow. And I'm going to adjust this graph a little bit. So 1, 2 is here. That's v. Minus 1, 3 is here. OK? And based on this algebra calculation, the vector that is called v plus w is the vector 0, 5. That is to say, the x-coordinate is 0, 1, 2, 3, 4, 5. OK? Now this is nice because observe that I can sort of think of this addition now geometrically. I can say, OK, so I start with v. I'm going from 0 to 1, 3. And then once I'm here, I'm going to be using this vector to move. And so if I were to sort of take this vector and attach it to the end, it would end at the end result. Or I could have done it vice versa. Right? I could have started with w and added to it v. And that is to say, vector addition geometrically corresponds to taking the arrows and gluing them beginning to end. So okay. Now in higher dimensions, it's not as straightforward to visualize it like this, but the same idea holds. And in a sense, by sort of like generalizing or by sort of extrapolating this analogy between the geometry or correspondence between geometry and algebra, we can sort of like start imagining how 16-dimension could look like. Of course, there are certain visualization methods, but for now, let's just focus on 2 dimensions. This is vector addition. How about vector multiplication? Scalar multiplication. Let me take another vector. let's say B is 2 minus 3, and C is, actually, let me do this. OK, C is 1 over 2. OK, let me say C1. C2 is 2. Let's do it like this. So again, I need to first draw, let's first do the algebra. So C1 times V is by definition 1 over 2 times 2 minus 3. And based on this definition over here, the way I compute this vector is by basically distributing this number over here to the entries. So that the first entry is 1, and the second entry is minus 3 over 2. This is this new vector. And then the second vector, which I would get by scaling V by C2, is 2 times this. And again, I distribute to get 4 minus 6. OK, so now geometrically, no, I did it wrong. Sorry. 1, 2, 1, 2, 3. First coordinate is 2. Second coordinate is minus 3. So this is the endpoint. And my vector, again, is represented by, sorry about this. I'm just going to change it again. OK, so 2 against 3 is over here. That's my vector, my original vector. Now, if I were to look at this, this is just going to have the same entries, but scaled by a factor of 1 over 2. That is to say, I take this vector, shrink it to get this new vector. And it's going to be exactly this. So this is going to be C1 times V. And then to get this, I do the same thing, but this time I'm expanding, right? So that the entries are going to be 1, 2, 3, 4. And then 1, 2, 3, 4, 5, 6. OK? Now, of course, you could combine this scalar multiplication and vector addition operations to sort of like build more and more complicated expressions. And the geometry would sort of like continue. And you would be able to keep using the geometry as a sort of like intuition pump. Not only in 2 dimensions, but also in higher dimensions. And again, let me just emphasize here that really these 2 operations, again, when considered geometrically, are clearly generalizations of this and this. OK? It just turns out that in this case, you don't have more than 1 dimension. So all you can do is to put vectors right next to each other along 1 dimension. And likewise here, all you can do is to scale vectors along 1 dimension. That is to say, R, or R to the 1, 2 is a vector space. Okay? We weren't calling it that, or you weren't calling it that when you were first learning arithmetic, but it is also a vector space. So let me write it here. So actually, That is to say, this notion of a vector space or vector addition and scalar multiplication are indeed true generalizations of number addition and multiplication. So, R or R to the 1, 2 is a vector space for this particular vector space. Number addition coincides with vector addition and number multiplication coincides with scalar multiplication. For it, number addition is the same thing as vector addition, because each vector has only one entry. That is to say, it's just a number. And number multiplication is the same thing as scalar multiplication. With the caveat that when you're multiplying two numbers, you're pretending that one of them has a unit and the other one doesn't. So only one number has a unit. Okay? Not both. Any questions about this? Now, in the remaining 7 minutes, or maybe 6, I'm going to introduce some further terminology. But of course, let me also mention that n equals 3, the same thing applies, same intuition, right? Now, instead of a plane, you have a three-dimensional space. Now, vectors can move in 3 dimensions. If you had n equals 4, you would have 4 dimensions. It's harder to imagine that, so that's why we're not really discussing that much. But it's still important for application purposes. Because you see, this allows you, so this sort of geometric interpretation of vectors and vector spaces allow you to sort of think of, for instance, data geometrically. So this is very important because as humans, we're well adapted to think geometrically. And so that provides a lot of intuition pump. So it provides a certain very good intuition pump. Of course, learning how to use that particular intuition pump is a different matter. I think that requires practice. But that's what this class is for, really. So 2 notions, linear combinations and linear span. If I have, let's say, p vectors, p many vectors, okay, in Rn, so each of these p vectors contain n possibly different numbers, okay? And I have, let's say, p numbers in R, so scalars, let me say, perhaps. Then if I write it in a certain way, write these, and if I combine them in a certain way, it's called a linear combination. And basically what I do is this. I use C1 to scale multiply V1, and likewise C2 for V2, and so on. And these give me new vectors, and then I can add all of them up. Okay? So that's a linear combination. By definition, it's a linear combination of V1 to VP. Linear combination of V1 to VP. That's the first definition. And the second definition is all those vectors that you can write as a linear combination of the pre-given vectors is called a linear span. So and this is denoted like this. You write span, and then you open curly brackets, v1, v2, dot, 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 vp, close curly brackets. This is going to be a certain collection, is the collection of all those vectors that can be written as C1 V1 plus C2 V2 and so on. So Ci here are arbitrary. You can use any numbers you want. I still have time. Okay. So how do I think of a linear combination geometrically? I think of it like this. Let's say I'm given two vectors. Let's say this, and I'm trying to move in 3 dimensions. And I look at sort of some scaled version of this vector, and I say to myself, I get to go that units in that direction. And then after I go that units in that direction, I can use this other vector, which is possibly in a different direction, some other units. Wherever I can reach is going to be the linear combination. And really, all those points that I can reach in this way are going to be called, or is going to be called the linear span. Now, we're going to spend some more time on this stuff. Unfortunately, I'm, I think, out of time. So this is all for today. Thank you. We don't have class on Monday next week, so I'll see you on Tuesday.